In this video, I will give some examples to illustrate the proof by contradiction. To prove that a proposition is true is sometimes easier to prove that its negation is false. Example, the implication, the proposition P implies Q. What is the negation of this proposition? The negation is P and not Q. Not Q is the negation of the Q proposition. What is the intuition of this negation? The intuition is that this P implies Q means that P gives Q, but here we have P and not Q. That means that P doesn't give Q. This is the negation of the implication. It's a conjunction of a proposition of the first proposition P with the negation of the proposition Q. To prove that P implies Q is true is sufficient to prove that P and not Q is false. I give example here. Let A and B positive real number. We want to show that if A over 1 plus B equal to B 1 over 1 plus A, then A equal to B. We have P, the proposition P, implies the proposition Q. So I do the negation of this proposition. Suppose that A over 1 plus B equal B over 1 plus A, that is P, and not Q. Q is A equal B, not Q is A not equal B. I will do some application and finish when I get a contradiction, because when I get a false thing, that means that what I suppose is not true, is false also. But if I get a true statement, I can't say anything, because the false can implies true, but the true doesn't implies false, because when I begin with a true statement, I finish with a true statement. So here I multiply the two members of the equality here by 1 plus B and 1 plus A. 1 plus B and 1 plus A are different from 0 because B is positive, and when I add 1, B plus 1 is strictly positive, then different to 0. 1 plus A also is strictly positive, so different to 0. Different from 0. So I can say that implies A times 1 plus A is equal B times 1 plus B. This implies that A plus A squared is equal to B plus B squared. I put B2 in the right hand side of the left side of the equality, A squared in the right side. So I can say a squared minus b squared equal to b minus a. This implies that I factor a squared minus b squared, a minus b factor I plus b equal minus a minus b. Since a is not equal to b here, then a minus b is not equal to 0. Then I can divide the equality by a minus b and get then a plus b equal minus 1. Contradiction. This is a contradiction because the sum of a positive number doesn't give a negative number, because a and b are positive. And this finish the proof. Here other examples. Exercise. Prove that the following statements are true. First statement: n is an integer number, positive integer number, if n squared is even, then n is even. Second statement: square root of 2 is not rational, don't belong to the irrational number. Third statement: square root 2 plus square root 3 is not a rational number. For the first statement, I use contraposition. Which means the given proposition is P implies Q is equivalent to the contraposition of this implication, which is not Q imply not P. I reverse the order of P and Q and do the negation. So if the contraposition is true, then the given proposition, the given implication is true also. But here I use the proof by contradiction, which means that the negation of the given proposition is false. So the given proposition is true. Notice that the difference between contraposition, the contraposition is true, but here the negation is false. First statement: by contraposition, I begin with n is not even, which means that n is odd. So this implies I can write n as 2k plus 1k, an integer number. This is how we write an integer, an odd number. 2k plus 1 with k is integer number. By squaring, I obtain n squared is 2k plus 1 squared, which implies that n squared equal to 4k squared plus 4k plus 1. I factor by 2, which equal to 2k squared plus 2k plus 1. factor here by 2, which can I write 2 times k prime plus 1, where k prime is an integer number, because k prime is 2k squared plus 2k is the sum of 2 positive integers. This is how we write odd number. So n squared is odd. The contraposition of the given proposition is true. So the given proposition is true also. Second proposition, I use proof by contradiction. The proposition is square root 2 is not rational. The negation is square root 2 belongs to Q, is rational. We suppose that, so we can write square root 2 as fraction between two integers, a over b, where a is an integer number and b is also an integer number but not equal to 0. And I suppose that a and b is irreducible, is not reducible fraction, that a and b have no divisor other than 1, which can I write like great common divisor of a and b is 1, no other divisor other than 1. I squared this equality, which gives 2 equal a squared over b squared. Then a squared equal to b squared. A squared is 2 times an integer number. Then a squared is even. I use the first statement. When n squared is even, n is even. So a is even. I can then write a is 2k, where k is an integer. This is how we write the even numbers. So I use this equality here. A squared is equal to b squared. I cancel by 2. Then I find 2k squared equal b squared. B squared is 2 times an integer. Then b squared is even. I use again the first statement. N squared is even, then n is even, b squared is even, then b is even. I found that a and b are both even. This is contradiction, because we say that the great common divisor of a, b is 1. They not have other divisors other than 1, but here 2 is the divisor of a and of b. This contradiction proves that the supposition here is false, and so the given proposition is true. Third statement I use also proved by contradiction. I suppose then square 2 plus square 3 is a rational number. I use a well-known property of rational number, that if a is a rational number, not equal to 0, then the inverse of A is also a rational number. And also the sum or difference between two rational numbers is a rational number. And I put A is equal to square 2 plus square 3, which is a rational number and not equal to 0. So A minus 1 over A is square 2 plus square 3 minus 1 over A. A is square 2 plus square 3, which belong to Q. This A minus 1 by A belongs to Q. Here I multiply denominator and numerator by the conjugated expression of square root 2 plus square root 3, and it gives square root 2 plus square root 3 minus 1 over square root 2 plus square root 3 times square root 2 minus square root 3 times square root 2 minus square root 3. This is the conjugate expression of square root 2 plus square root 3. This gives minus 1 because A plus B times A minus B is A squared minus B squared. Here square root 2 squared is equal to square root 3 squared is 3. 2 minus 3 is minus 1. So this belongs to Q. So this one is square root plus square root 3 minus, here is minus 1, and with this minus 1 give plus square root 3 more square root 3, square root 2 minus square root 3 is belong to Q. I cancel here and it gives 2 square 2 belong to Q. And we know that if a rational number is divided by 2, the result is a rational number. So I divide by 2 and then square root 2 belong to Q, which contradict the second statement. So what we suppose, the supposition here is false, and then the given proposition is true.